Functions. We introduced pointers last time and some basic usage of them. We saw how we could use that to finally solve that swapping problem where before we tried to create this swap function that took two variables 10 and 20 and tried to swap them, but we saw that that wouldn't work because they were being passed by value. 10 and 20 were being copied and the copies were successfully swapped, but the original values were not. We solved that problem by using pointers. We gave the pointers to those two variables that referred back to the original variables so that they could be swapped. Right? Now we're going to look at more use cases for pointers. First of all, one that you're already familiar with, right? Scanf, that we already talked about. Scanf, right? In this, remember what you use with scanf? You use the ampersand, right? The ampersand is the and thing there, to pass a variable by reference, so that the function can manipulate it. Manipulate it, right? There we go. So what if it didn't do that, right? What if we passed by value? Here's x, right? Say x has the value 10. We pass off a copy of x, 10, to scanf, and it's able to read the input from the keyboard masher, right? They enter 123 instead of 10. Well, now what do I do with 123? Right? If I change the copy, that the original value that you wanted to fill, right? That's I don't have access to that. So if I gave you a pointer to that variable, though, you can take that 123 and you can put it into that bucket. You can put it into the memory contents that I'm pointing to. Right? And so passing by reference allows a function to manipulate your variables. Right? Now we're going to look at another one, right? Another use case for this. With pass by reference, you can return multiple values. So what do I mean by that? Remember what a function is, right? A function, say, in mathematics. Does a function have more than one value? No, it would fail the vertical line test. The unit circle is the typical example, right? One x value maps to two other values, right? Above and below. That's not a function, right? That would be returning two values. Likewise, in C and in all programming languages that I know of, if you have a function, you can't return multiple things. Right? So how are we going to return multiple values in this case? What we're going to do is we're going to pass buckets. Right? We're going to pass pointers to variables that we want the values set. That way we're going to be able to return multiple values from a function. So for example, let's go ahead and go through another toy example here that we're going to be easily familiar with here. What if I had a radius? Right? A radius of, I don't know, 1.0. Tell me what you know about a circle's area, and tell me what you know about the circle's circumference with that radius value. How do I compute an area? Pi r squared. So what kind of pi should I be using? 3.14159? No. What? Don't use your own pi. Do what? M sub pi. Right? Pi r squared, pow, radius squared. You can do that. We would not take off points for that. But even well, we would take off points for not multiplying, but we're not going to take off points for using the pow function. That's perfectly fine to do that, but even the compiler knows you shouldn't be doing that, right? X raised to the power y, there's some complex mathematics going on under the hood there. And your compiler will see you just wanted to raise it to 2. I'm going to replace your code with radius times radius, right? Which is much more efficient and doesn't even require the math library at that point. Right? That's what I'm going to leave it as, though. Right? Either way is perfectly fine as far as scores go. Right? But using your own pi is definitely not fine. Tell me about circumference. Circumference is the distance around the outside of the circle. How do you compute circumference? 2 pi r, so pi d, d being the diameter. So in this case, it's going to be 2 pi r times 2 times radius. Right, there we go. Right. And another tip here. Is that an appropriate variable name for a radius? No, right? If you're in mathematics, sure, fine, right? But we can afford better variable names here, okay? All right, well, I can compute those two things. Now what I want to do is I want a repeatable function to do this for me. If I were to make these functions, what would it look like? Double get area given the double radius, right? And I would have to make another function, double get circumference, right? Double radius. Just like you had to do yesterday in your lab, right? You had to do 3 sepia functions, one for red, one for blue, one for green. Why did you have to do that? Because you're only able to return one value. I need 3 though. I need red, green, and blue. Well, you're gonna have to write 3 functions. But now that we've got pointers, we don't have to do that. We could write one function. And that's what you're gonna do next week, right? So reuse your code from this week. I'm not going to write 2 functions here. I'm going to write one function. I'm going to write one function that compute circle statistics for short, that takes a radius. Right? And it will take other things. I'm not going to return one value, right? If I return the area, then I would not be able to return the radius. If I return the circumference. If I return the circumference, I would not be able to return the radius, or the area, whichever one, right? So what I want to do is I want to make 2 variables here that are passed by reference. Area and circumference. They're passed by reference because they're not regular old variables, right? Radius is a regular old variable, double. But what type of variable is area? A pointer to a double. Right? Likewise, circumference is a pointer to a double. Now, if I'm using these 2 values to put those 2 values into those 2 variables, I don't need to return anything at all anymore. If I'm not going to return anything, what keyword do I use? Nothing? Void. Void functions return nothing. Okay. What else should I be doing now that I'm writing functions? To do documentation. Right? Make sure that you're doing your documentation. There's my prototype. That doesn't actually define what the function does. Later on, I need to provide an actual definition. Now, if you were doing this modularly, this would go into a header file. This would go into a source file, and separate files everywhere, just like you did in your lab yesterday. Right? All right, I want to compute the circle statistics here, so I'm going to move this stuff down here. Right? Except that I can't have 2 variables named area. I can't have 2 variables named circumference. And so I'll go ahead and do that. Is that going to work? Let's try to compile this and see what the compiler says about this. Error. Oops. I know I have math. M pi times radius. Oh, sorry, it's down here, right? So error. Incompatible types. We have a double here, and then we have a double star. In other words, one of these things on the left, on one side is a pointer. One of these things on the other side is not a pointer, right? They don't match. The thing on the left-hand side, what is that? Area is a pointer. The thing on the right-hand side is not a pointer, right? It's a number, right? So how do we make these 2 things compatible? We go back to the post-it note where we've written these 2 things down, right? A pointer variable, to make a pointer variable into a regular old variable, we use the dereferencing operator. To make a regular old variable into a pointer, we use the referencing operator. I have a pointer variable here, so which one do I use? Star. Right? Likewise, down here, same thing. I dereference it so that I can put an actual value into it. Okay? Now I can use one function and only one function to get both of those values at the same time. Compute circle stats. I'll go ahead and do it like this. Get rid of that and get rid of that. And then I'll call my function with radius, area, and circumference. There we go. So now those 2 errors should go away, but I get new errors here now. I get an error on line 19. Once again, what does this expect? A regular old variable. Area, is that a regular old variable? Nope. But this area is a regular old variable. So I've got a regular old variable that needs to become a pointer variable. So again, I look at my post-it note. To make a regular old variable into a memory address, a pointer, what do I use? Ampersand. Oops, area. And ampersand circumference. And all the errors should be gone at this point. And of course, you can print that out, right? Printf the area and circumference are %f and %f. Right, end the line. Area circumference. And if I spelled everything correctly, it should compile and run. So with a unit circle, it all just becomes pi, right? Pi and 2 pi and 2 pi. So I'm pretty sure that those are correct. Okay. So I can have one function to compute multiple results. I could have one function to compute the R, G, and B values of a sepia tone filter all at once without having to resort to 3 different functions and then bringing those 3 functions together. Okay? Let's do the same thing with our finance example that we've been working with. Right? So get monthly payment returns one value. Right? You're not limited to just multiple values. Right? Even if you only have one result, it still might be a good idea to return, double quotes here, to return a value using a pass by reference variable. And we're going to see why here in a moment. Okay. First, let's go through the exercise of changing our function here, this loan finance library that we built here. Let's change get monthly payment so that we are not returning that value. Instead, we are putting it into a bucket represented by a pointer. Right? So double star, and then what's the result here? Monthly payment. Monthly payment. There we go. And I'm going to change this so that it doesn't return anything, and we'll come back to that. Right? Because now this basically doing this frees up our return value here, right? And we're going to use that later. Okay. Now I no longer return anything. Instead, what do? Star, so that monthly payment, which is passed by reference now, receives this final value that you've computed up here. I can't declare it here, so what I'm going to do is I'm going to rename this result, and result, and then at the very end, I will dereference monthly payment, and I will set it equal to the result. Just because I don't want, I'm using it like 3 times up here, 1, 2, 3, right? I don't want to confuse it with the monthly payment here, so I'll temporarily put it into a temporary variable, and then only at the very end will I dereference it and set it. So I'm only doing it once. Okay. Okay. What else do I need to change if I've changed the signature of this function? I've changed the return type. I've changed the number of parameters. Before it was only taking 3, now it's taking 4. I need to change also the prototype. There we go. And now they match. What if I didn't do that? What would the compiler say now? How do I compile without creating an executable? -c, and it's finance.o, or .c, excuse me. There we go. Error, conflicting types. You said that monthly payment took a double and received three values, a double, and an integer. But over here, when you defined it, you changed that, right? Now it doesn't return anything, and it takes 4 parameters instead. There is a mismatch here. Error, conflicting types. They've got to be the same. Can I redo? Oops. Nope. That's a Firefox thing. All right. So there we go. And now they match. When I compile this, it should be all right now. All right. I should also update my documentation here, right? Computes the monthly loan payment based on the given inputs, right? And places the result in the pass by reference variable monthly payment. Okay. Now let's think about this a little bit. I'm taking an annual percentage rate, and I'm saying that it's in the documentation. I'm saying that it's on the scale of 0 to 1. The principal, the loan amount. Is there an invalid loan amount? Remember when we were doing this exercise? Can you borrow negative $1,000? I mean, you can, but then you're depositing it, right? That doesn't make any sense. You can borrow $0, but that doesn't make that. There's no point in that, right? What about the number of years to pay the loan back on a monthly basis? What would be an invalid value there? You have 0 time to pay it back, right? That could go wrong, right? So we've got a whole bunch of things here that could be an error. Let's do some error handling now. Right? How would we deal with that over here in this function? So, question, what if they gave us an invalid annual rate? In other words, something outside of 0 to 1. I guess they could get like 200%, and that would be valid for like loan sharks or something like that. It's definitely not legal, right? Even something above like 20 or 30% is not legal, right? Depending on the state. So what if they gave us an invalid result? What would you do? What's one thing we could do? We could tell them, right? If annual rate is less than 0, or annual rate is greater than 1, then we shouldn't allow this, right? This is an error. We could tell the user, printf error, rate must be between 0 and 1. End the line. What's something else we could do? What have we been doing in main this entire time if something bad happens? What did you do in main in your exam? The vast majority of you got it right.
Exit.
You quit, right? Exit. And then a lot of you put 1 because that's the example that we've been giving you, right? Now we're going to give meaning to that 1 by the end of the day, okay? What's another error condition here? What was the error condition with principal? Principal cannot be 0 or negative, sure, right? And I'll go ahead and print out another error message here. The principal must be positive. There we go. And I'll exit with maybe a different error code because a different type of error occurred, right? Okay. Else if years is less than or equal to 0, then I'll print a different error message with a different error code, right? Years must be positive. There we go. What's something else that could kill this program? When we were talking about pointers on Monday, what's something that caused a seg fault with a pointer? All right, I'm going to ask Bret Hart to come in here and whap everybody upside the head. What did he say? Don't dereference a null pointer. Right? So, in tribute to Bret Hart here, else if monthly payment, he's still alive, by the way, right? And he can do it. Right? If you pay him enough money, maybe he'll come and do it. Right? There we go. If the monthly payment is null, then error, something happened with memory. Right? Something bad happened with memory. That's another error condition. What if this were null? What would I be doing down here? I would be dereferencing it, leading to a segmentation fault. All right. So those are all error conditions. Now let's think about our approach here. This approach has been fine up till now because we've been doing everything in the main. If somebody doesn't give us enough command line arguments, fine, we quit. If somebody gives us bad command line arguments, negative values, we quit, right? Because there's no real way that we can recover from that. But we're inside of different function now, right? Should we quit? Should we be printing anything? Let's think about that. And for our direction, let's think about what we already know. The math library. If you give -1 to the square root function, does it say anything? Does it print anything? Error, you can't call the square root function with a negative value. No, it doesn't. Does it quit out of the entire program if you try to compute a square root of -1? No. It just results in not a number. This is not the strategy that we're going to take going forward, right? This is fine in main, but this is not fine for a library of functions like get monthly payment or financial functions, right? Instead, what we're going to do is we're going to communicate back to the calling function that something happened. Right? We're not able to compute the monthly payment because you gave us bad input here. And now that we're returning this value by reference, right? Returning it by reference, that means that we've freed up the return type over here. What if instead of printing something out and saying something happened, and then exiting with an error code. What if we just returned that error code? Right? So I'm going to come back over here and document that. Right? If an error occurs, the function returns a non-zero error code indicating the type of error that occurred. Okay? So let's go back over to our code here and change it so that it does that. Instead of taking the decision away from you, this library is going to say, all right, you gave me a bad annual rate. I don't know what to do with that. Right? I'm not going to tell you, I'm not going to print anything out to the standard output. I'm not going to kill your entire program. I'm simply going to return 1 to you. Something bad happened. Something bad of type 1 happened here. Right? Something bad happened of type 2 here. Return 2. Something bad happened of type 3. And something bad happened of type 4. All right, there we go. So now the power is with you, right? The decision-making process is on whoever called this function. If we decided to, in this function, if we decided to exit, we're taking the decision-making process away from you. If square root exited every time that you gave it a negative value and killed your entire program, that's not very flexible, right? It's taking the decision-making process away from you and placing it into the math library. We're not going to take that decision-making process away from anybody that wants to use our finance library, right? Instead, we're going to say, look, I can't, you gave me a bad annual rate. You gave me a bad principal here. You gave me a bad years, or you gave me bad memory. I'm not able to process, so I'm not going to process. Instead, I'm simply going to return immediately from this function, right? And give you some information. Something bad happened of type 1. Something bad happened of type 2. What if nothing bad happens? So what do you do at the end of main? Return 0. Why? Because everything was great, right? So this is consistent with the rest of C. What is false in C? 0. What is true in C? 1. What else is true in C? Any number that's not 0. 2, 3, 4, 5. You're not running out of any numbers anytime soon here, right? So that's the pattern that we're following. Question: did an error occur when I called the function getMonthlyPayment? False. No error occurred. True. An error occurred of type 1. True. An error occurred of type 2. True. An error occurred of type 3, etc. It follows that same pattern, okay? And that goes to what's called error handling. So why would you want to do this? It's because it frees up the return value so that you can use it for proper error handling. Right? How do we do that? To do that, I'm going to have to start a new note set here. Sorry, I should have done this before. Error handling. MD. There we go. And there we go. Error handling. Close this note set and start a new one. There we go. All right. So what kind of errors can occur in a computer, right, in general? So you've seen, like, say, the blue screen of death, right? If you're a Windows user, right? If Windows just completely craps out, what happens? This blue screen comes up with a bunch of memory and stuff that end users don't know anything about, and they have to file a report on, right? Et cetera, et cetera. What else? What other kinds of errors could there be? Somebody could come along and kick out our power cord, right? And if we don't have a battery or a battery backup or a generator backup or something like that, right? Then we're kind of cooked, right? Errors can either be completely unexpected or anticipated but not normal. In other words, can you write any software that will reach out and plug it back in if somebody kicks out the power cord? No. There are some errors that you just can't handle. But there are some errors that you can anticipate, right? Some of them should be fatal, right? The program in general should die from them. Right? For example, if you've got an application that is making a connection to a database server, And you need that database data in order to process the data in your application, right? Well, there's not much you can do if you don't have internet access, right? You can't write software to troubleshoot your own internet connection, right? That's a completely different. That's a problem that's outside of your program that you can't deal with, right? So some errors by nature are fatal, right? You can't reach out of the computer and slap the user and say, "Don't give me a negative annual percentage rate," right? You can just tell them, something happened. You're gonna have to try again, right? But some errors you can recover from, right? You can anticipate these errors, and you can write code that in the event of that error, I want you to do this process over here instead, right? And do something else instead of the normal control flow. This entire process is known as error handling, right? Once you see an error, you decide how to handle that error. How do we do this in C? C uses what's called defensive programming. Right? It's a philosophy of look before you leap. Right? It wasn't that common, but on the exam and a couple of other hacks, we've seen this pattern before of checking for command line arguments after you've attempted to use them. Does that sound right? So I need 3 command line arguments. How do I check for that? Are there 4 command line arguments? Right? After I've checked, yes, there are enough command line arguments. Then you can go ahead and go get them. Right? What if I leapt before I looked? Right? I'll just go ahead and grab those 3 command line arguments. Then later on, I'll check, were there 3 command line arguments? Does that make any sense? No. You are leaping before you look. If you're about to go up on a precipice, right? There's a ledge there, right? What do? You look before you take another step. Am I about to fall off the edge of this cliff? Right? You don't jump off the cliff and say, if you safely land, go, oh, good, phew, I was able to make that leap, right? Or on your way down, plummeting, oh, oops, I made a mistake, right? Is there any way to recover from that? No. You look before you leap. You do error handling before you attempt to look at those values, right? So you write code to detect potentially dangerous operations. As an example, right? So suppose that I've got some code here, and let me give myself some more room here. Text. There we go. I've got int a and b, or let's make them double so there's no truncation here. A and b, right? And eventually I want to go, to do read values in ... And I'm going to go ahead and go with another variable here. X is equal to a divided by b. Right? What's a potential dangerous thing that could be going on here?
B was 0.
If b is 0, what's going to happen? It's not going to crash the program, but it's going to result in not a number or something like that. It's going to end up with a bad value. Right? What if instead I looked before I leaped? Right? If b is 0, then don't divide it. Right? If it's not 0, then go ahead. Say x is equal to a divided by b. Right? Right? If it's 0, though, don't divide. Right? Do something else. Right? Something else. There we go. That's error handling. You look before you do that potentially dangerous code. You look to make sure, do I have 3 command line arguments before I call a to I or a to f in order to convert them? If they don't exist, how could I call that function? Right? And that would lead to a segmentation fault if you didn't. Right? Okay. So the philosophy is if an error condition is detected, you don't do the potentially dangerous code. Instead, from a function, you return, you immediately return without doing the dangerous code, and you return an error code to the calling function to communicate the type of error that occurred. Right? You don't, I'm going to emphasize this, you don't exit the program. You don't print anything. Right? you simply return with an error code. The calling function then has the responsibility or option to deal with the problem or error. That's what error handling is. If you don't do this, if you exit the program, there's no handling to be done. Right? It's an error, and then it's fatal, and it's done. It's over. There's nothing to handle there. Right? Proper error handling is when you just simply communicate the problem back to the responsible party. Right? I don't know. A computer. One of the lab. Well, when I was a grad student, I was in a lab one time as a TA, and one of the monitors started smoking. Right. So was it my responsibility to go over there and fix it? No. I handled that error by telling the appropriate people, and they came in and they took care of the problem. Right. I didn't handle it myself because I didn't want to deal with that. Right. It's not my responsibility. Right. So don't handle it yourself either. Right. Let somebody who is responsible handle it. You don't exit the program. You don't print anything. You don't exit the program because that takes the responsibility away from everybody else. That takes the flexibility away from everybody else. You don't print anything either, though, right? Why don't you print anything? What if you did print something, right? Imagine if the thousands of lines of code that you're actually invoking when you call a standard library, imagine that they were printing all this stuff all the time. Would you ever see your actual output? No, right? We don't want to print anything because the vast majority of software is not written for humans, right? Everything that we've been doing in this course up to this point is because it has been for humans, right? We've got some basic output here, but that's not what real software is all about. 99% of all software is written for interface software called glue code, where you've got one system and another system, and you simply need to make these systems talk to each other, right? So do you want a human in between getting in the way of massive data transfers? No, right? That defeats the whole purpose of writing a program. That defeats the whole purpose of automation. If we have somebody literally sitting at a screen waiting for something to happen all the time, that kind of defeats the whole purpose of writing software, right? So instead of printing something, there's no human sitting there like watching and saying, "Oh, okay, something happened. I need to jump into action now," right? We don't do that. We have logs, right? We have system logs that do, save a bunch of stuff to the system log so that if something does happen, somebody can come back in the morning and say, well, something bad happened at 5 a.m. This morning, right? Okay, well, I'll check the system logs. Okay, look. Okay, looks like something was wrong with this system over here. Go over there and diagnose it, right? But that's after the fact. Nobody is sitting there at 5 a.m. staring at all the logs coming, the millions of lines of logs that are coming out and waiting for just the right output to jump into action and do something, right? That's not how computers work. So you don't print anything, you don't exit the program. So how do we do this in C, right? Again, you just return an error code, right? To do this, make all of your result values as pass by reference variables. Then use the return type to return an integer, right? Int that indicates the type of error that occurred. And by convention 0 indicates no error. False, no error. Non-zero indicates yes, there was an error. Right? And then you're not going to run out of numbers anytime soon. 1, 2, 3, 4. If you identify a new error condition that you want to handle, then go up to 5. Right? You're not going to run out of numbers anytime soon. You don't use doubles because doubles are not precise. Right? We've already seen that 1/3 times 1/3 plus 1/3 plus 1/3 is not equal to 1, right? But 1 is always equal to 1 as an integer. 2 is always equal to 2. 3 is always equal to 3, right? We'll not have any of those issues, any of those floating point issues, if we stay away from floating points, right? All right. So come back a month from now, right? In fact, maybe even just 5 minutes ago when we wrote this stuff. What was error code 3 again? Does anybody have a good memory here?
Negative years.
Okay, negative years. Thank you. I literally did not remember, and I wrote it just now. Right? All right. What was error code 1? Yeah. What was error code 4? Was there a 5th error code? I don't remember. Right? Yeah. Are you going to remember those magic numbers? Nope. We've seen magic numbers before, right? Magic numbers that came out of the air. 1.609. It's now literally been 4 weeks. Do you remember what that number was? Exactly. Right? Well, maybe some of you do. What was it? Kilometers per mile, right? So, how could we get a more human-readable term to indicate these error codes instead of using these magic numbers? How did we do it with KMS per mile? We used define. Define annual rate out of range error. Right? It's kind of long, but so be it. Right? And I'll define that to be 1. Define negative principal, or non-positive negative. I'll go with negative principal. Principal error. And I'll define that as 2. I will define negative year error as 3. I'll define null pointer error as 4. Right? And now I don't have to use these mysterious magical numbers anymore, right? I can just go ahead and use a human-readable term for this. Right, there we go. There we go. Negative year error and null pointer error. There. Problem solved. Do you need to remember what 1 was, what 2 was, what 3 was? Nope. And in fact, what if I wanted to switch these around? Doesn't matter. I don't have to change any of my code. What if I want to add a new one? Doesn't matter. I don't have to change any of my code except to add that the error handling for that specific error condition, right? This can get kind of unwieldy though, right? For example, what if one library has a bunch of errors and another library has a bunch of errors and they both have null pointer error, but one of them is 4 and one of them is 8, right? This is perfectly fine to do it this way, by the way, but I'm going to show you another way. And another solution is to use enumerated types. So you could define macros using the define syntax that we've used before, error type, and then you can set it to 1 or whatever, right? You could do that. Right? And in fact, POSIX errors, that's exactly how it works, and I'll show you that on Friday probably. Or you can use an enumerated type. Let me emphasize that. There we go. All right. So what is an enumeration? An enumeration is just a list. For example, days of the week, right? 7 days of the week. What's the first one? It's not a trick question. There was controversy in this morning's class. Some people said what? Sunday. Other people said Monday, right? And unfortunately, it does cause problems. When I went to set all the due dates for Zybooks, their calendar, for some inexplicable reason, started on Monday. So I knew that I wanted to set everything due on Mondays. So what did I do? I chose the second day, which happened to be Tuesday. Thankfully, I caught most of those errors before the semester started, but it caused a huge amount of confusion, right? But that's an enumeration. Sunday, whether you start on Monday or Sunday, it doesn't matter. There are 7 days of the week, and they ain't making any more, right? There are 12 months in the year, and they ain't making any more, right? There are 4 errors here, right? And I've identified all of them, right? Anything that's in a list that is fixed, that is probably not going to change, is an enumeration, right? An enumeration is simply a list, a day of the week, months, or error codes, right? In C, you can define an enumeration, a list, as follows. Let me do it for the days of the week first. I start with type def. Type def. What do you think that's short for? I'm defining a type of variable, and so def is definition. Type def, all one word. enum. Enum is short for enumeration. I open it with curly brackets. I close it with curly brackets. Within that, I provide the list of things that I want to enumerate. I'll go ahead and go with Sunday. It starts on a Sunday. Right? Monday. Anybody who said Monday is wrong, right? No, you're not wrong, but somebody who said Tuesday was probably very wrong. Tuesday, Wednesday, Thursday. Note what I'm doing here. How am I naming these things? All caps. Right? If there were multiple words, like over here, annual rate out of range error, what did I do? All caps, separating each word with an underscore. In coding, this is kind of coding's versions of the Oxford comma, right? The Oxford comma is optional. You can leave that, or you can don't have to put it there. Some people like to put it there, even though it's the last thing in the list, simply because if they come back and they add something, they made a new day of the week. Now we've got an 8-day week calendar or something, right? Then you're set. You don't have to put that comma in there. Some people just want it to be consistent. There's commas after everything. If you put it there or not, it's up to you. Just be consistent about it. All right? At the very end, I need to give this thing a name. Well, what does it represent? It represents the day of the week. All right? And I end it all with a semicolon. Now, later on in your program, you can use your own type. Right? For example, if I wanted to create an integer x, I can do it like this. But now, day of the week is a type. I can create a day of week variable, call it today, and I can set it equal to one of those things. What is today? Wednesday? There you go. Because I've defined my own enumerated type, I can use all of these keywords, and I have this type of variable right here, this day of week variable. So let's make some observations about the style observations, right? Or style or syntax style / syntax observations. There we go. So first of all, you use typedef enum to define a list, an enumeration. Within the opening, closing curly brackets, you have the list. One item to a line, separated by commas. Right? There we go. Whether or not you have that last comma, it's up to you. Values, use an upper underscore naming convention. Right? That's what we're going to require. Sure, require. If you're going to do an enumerated type, or if you're going to do a def, you should follow that convention. Right? At the end, you give your type a name, followed by a semicolon. Right? The name should be upper camel cased. Right? Day of week. That's a modern convention that I'm following. There are some other old school conventions that people follow, or they even use underscore casing, and then at the end they put underscore T to emphasize that it's actually a type. Don't do that. That is a built-in type. That's you might have seen it before from a previous lab. Like there's a type for date, and it's like date underscore T. That's a convention that the standard libraries use. You're not writing anything for the standard libraries, so don't use their convention. Right? Use this modern convention. It's upper camel cased. What would it look like, say, for the months? Let's do one really quick. Typedef enum. Oops, sorry. This should be C. There we go. Typedef enum. So, give myself some more room here. There we go. Now you don't have the luxury of looking at the other one as an example here. All right. Typedef enum. I open it with curly brackets, close it with curly brackets. So if I'm using this for months, what should I call it? First of all, should I pluralize it? Did I pluralize this one? Day of week? No. Month of year you could use, or you could just simply call it what it is. Month, right? All right, so hopefully there's not a controversy here. What's the first month? January. All right, there we go. January, February, right? Maybe there's a controversy because I like to use abbreviations. Mar instead of March, right? April, et cetera, et cetera. I'll let you finish that off, right? All right, questions about this so far? No? Then let's come over here and not use this convention. Let's use an enumerated type. So let me go ahead and define an enumerated type here for all my values. Type def, enum, and these things right here. Annual rate out of range, get rid of that. Also, another observation that I didn't write down, what am I doing inside the brackets? Indenting, right? And I'll call this error type. Type of error, error type, whatever you want, right? That's not the correct syntax though. What do? Comma, 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 comma. Right? But now that, or you can leave that off one, right? But now this gets into how this is actually implemented. Right? The way that this is implemented is still by using integers. All this is syntactic sugar. What is syntactic sugar? We like to add sugar to our language, right? We like it to be a little bit more tasty, right? Because we want it to be a little bit more flexible, right? We want it to be more user-friendly, more human-friendly. So we like to add syntactic sugar, and that's what this is. All this is doing is creating a bunch of keywords, annual rate out of range error, but it's still under the hood. If you were to open this up and actually look at the code, it's still assigning an integer value to this thing. Right? The problem is, where does it start? This is the first one, this is the second one, this is the third one, this is the fourth one. As with everything in computer science, what ends up happening is it ends up starting at 0. Right? That's not what we wanted. What did we want no error to be? We wanted that to be 0. So if I'm going to do this with error codes, then I need to start with another dummy error code. The no error code. No error. Now this one will be 0. This one will be 1, 2, 3, 4. That has a problem when we do something like days of the week. What is the first day of the week? Sunday? It ends up being 0. What ends up being Saturday? 6. So what is Saturday plus Wednesday, since these are integers? Does that make any sense conceptually? If I asked you, what is Saturday plus Wednesday? That doesn't make any sense. But because these are integers, it makes sense. Saturday, you said, was 6. What would Wednesday be? 0, 1, 2, 3, right? Because it starts at 0, 1, 2, 3. So 6 plus 3 is 9. Which one of these things is 9? None of them, right? It doesn't make sense here either. So you've got to be careful about how you use this stuff. We'll review that on Friday, and then we'll talk about how C does this under the hood, basically. Right?